automorphisms of a field K is nothing but set of isomorphisms from the field K to itself. So this forms a group. So automorphisms of K which fix a field F is written like this. This set of isomorphisms again from K to K, but which fix a field F. So this field F, this lies within this K. So say you have a sigma which is an automorphism from K to K. So if it fixes F, if you restrict it to this subfield F, this is just an ID map. So it does not change the elements of the subfield F. Now these automorphisms of K, they form a group. And automorphisms of K which fix F, they form a subgroup. So this is a subgroup of this. So automorphisms which fix F is a subgroup of all the automorphisms. So we come to the first proposition. So the first proposition basically says you have an algebraic field extension K over F, and you have A which lies in this big field K, which satisfies the following equation. So say this is the equation of some polynomial F. So this is f of x, and each Ci is an element of F. So basically we are saying this polynomial F lies in f of x. So coefficients are taken from the field F. So if A is the root of this polynomial, so A is the root of F, so you plug in A here, this is equal to 0, then sigma A also satisfies the above equation. So if A is the root of F, then sigma A is also the root of F, where sigma is the automorphism which fixes F. So the idea is this, that this group, when it acts on irreducible polynomials like this, it will permute the roots of irreducible polynomials. So the proof is easy to see. You have this F and you want it to be equal to 0 so that you can plug in a root. So you plug in a root an and this will become equal to 0. So initially you started with some polynomial f in f of x. We want this f to be 0. So you have a root here. Now you apply sigma to it. So we're just putting sigma in front of all the terms. Now sigma, this is a homomorphism. In fact, this is a set of isomorphisms here, but this acts like a homomorphism. So sigma of 0 is 0. This will fix all these C's because C's lie in the field F. So this C comes right here, this C1 comes right here, this C0 comes right here. But since it's a homomorphism, then this multiplicative property of homomorphism holds. So by multiplicative property, this sigma goes inside. So this sigma which was here, this fixes Cn minus 1, this goes inside, this goes inside. So sigma of, so we are basically saying sigma of an becomes sigma a of n. So this goes inside. And therefore now you can see that now sigma a is the root of this polynomial f, because if you plug in sigma a here, you get this equation which is equal to 0. So the idea was that if a is root of this polynomial f, which is in f of x, then sigma a is also root of f. So because the sigma which is fixes the coefficients, this just permutes the root of irreducible polynomials. So we have gone from here to here. So that is, you have some extension, a field extension here, and corresponding to this extension you can construct this group here, and this group, when it acts on the polynomials, will just permute the roots. Now let us see some example of these automorphisms. So say C over R. So this is an extension. So this is just a cyclic group of order 2. Cyclic group of order 2 means Z by 2Z, which you can write it as 0, 1. So this is easy to see. So C over R looks like A plus complex IB, where A and B are real numbers. So you apply sigma to it. It has to fix A and B because this automorphism fixes real numbers. So A and B are fixed, so I can only be sent to plus I or minus I. So since there are only two possibilities, it's cyclic group of order 2. Then automorphisms of Q root 2 over Q. So rationals So again, this rational root 2 over rationals is of the form a plus root 2 times b, where a and b are rationals. So again, you apply sigma to it. This rationals are the fixed field, so a and b are fixed. So a and b go where they have to go, that is, they are the same. And root 2 can only change, so root 2 can go to plus root 2 or minus root 2. So again, notice that the roots are getting permuted. So this is permuting the roots of irreducible polynomials. So you can see the irreducible polynomial here is x square minus 2. So the roots are getting permuted. Root 2 is sent to plus or minus root 2. So only two possibilities against cyclic group of order 2. Now you consider this root 2 root 3 over rationals. This is cyclic group 2 times cyclic group 2. So this is again root 2 is sent to plus minus root 2. So this corresponds to irreducible polynomial x square minus 2 over rationals adjoined with root 3. So roots are getting permuted here for this irreducible polynomial. So roots are permuted. Similarly here, root 3 is sent to plus or minus root 3, corresponding to irreducible polynomial this over rationals root 2. Now again, you can see that this is cyclic group 2. This generates the first group, and this root 3 getting to plus or minus root 3 gets to the second group. Notice that root 2 is not getting mapped to root 3, or root 2 is not getting mapped to minus root 3, or root 3 is not getting mapped to root 2 or minus root 2 because of these irreducible polynomials. This mapping precisely corresponds to permutation here. This mapping corresponds to permutation here because we have this proposition right here. So therefore we are avoiding the mapping from root 2 to root 3 and root 3 to root 2. So similarly, you can have this automorphisms of rationals adjoined with root 2, root 3, root 7 over rationals is C2, 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 cyclic group of order 2 times cyclic group of order 2 times cyclic group of order 2. So this you can again see. So this, the first cyclic group corresponds to root 2 going to plus minus root 2, and this again comes from x square minus 2. This is irreducible over our rationals and root 3 root 7. So similarly, you can talk about x square minus 3 and x square minus 7. So this will be irreducible over root 2 root 7, and similarly here root 2 root 3. And again here root 3 will go to plus minus root 3, 7 will go to plus minus root 7. So you will have these three cyclic groups. So say G is a subgroup of these automorphisms of K. So G is a subgroup of set of automorphisms. Then corresponding to G, you have this field K of G, that is precisely those elements of K which are fixed by this G acting on them. So some elements of K will get fixed. So sigma will act on this A in K and will just be A. So this what you get is a field, and this is called a fixed field. And you have to check this is a field. So this is easy to check. So say this var phi is an element of the group G. So and A, B are fixed by this var phi. So obviously by definition phi of A is A and phi of B is B. So you see sigma is in G, sigma of A is A. So then obviously phi of A plus minus B, this is just the homomorphism here property, and this is just the fixed property coming from here. Phi of A is A, phi of B is B. Phi of AB again the homomorphism property here, and then phi of A is A and phi of B is B. Similarly here. So you can see that if you take elements A, B, and you can find their inverses, products, and sum. So this is closed under all operations. So K of G is a field. And we have shown by taking two elements A and B in K of G and showing that all the properties are satisfied. So say there are two fields. This is the next proposition. There are two fields F1 and F2, and both lie in this big field K. This implies that automorphisms which fix F2, automorphisms of K which fix F2, is a subgroup of automorphisms of K which fix F1. So notice the inclusion reversion. F1 is contained in F2. This implies that the corresponding group K over F2 lies within automorphisms of K over F1. So F2 contains F1. Here the group corresponding to F2 lies within group corresponding to F1. Now this is kind of obvious that, if sigma, so if there is some sigma which fixes F2, then it obviously fixes F1 because F1 lies within F2. So sigma will obviously fix F1. So this sigma lying here which fixes F2 will obviously lie here. And similarly here, you have two groups, G1 and G2, and they are subgroups of automorphism of K. So corresponding to G2 you have a field KG2, and here you have KG1. So then KG2 lies within KG1 precisely because again you have sigma here. Since it's a subgroup of G2, this sigma will have to fix KG2 at the least, because G2 is fixing it. So any element sigma here which is in G1 also lies in G2 because G1 is a subgroup of G2. So this sigma has to fix KG2, and it could fix something more also, but it has to at the minimum fix KG2. So KG2 lies in KG1. Again notice the inclusion reversion. So G1 is a subgroup of G2 implies KG2 is a subgroup of KG1. So some kind of a contravariance happening here.